This is called a resistor divider, and both resistors have the same value. When we put a voltage at one end and ground at the other, then the voltage in the middle will be half of it. We can now put 8 volts at the ends and read 4 volts at the Arduino without burning it to the ground. Let's make the Arduino do some actual reading and send it to the serial monitor. Very nice. But we want a reading in volts. How do we do that? Well, I take 2 samples of both the actual voltage and the number the Arduino is measuring. On Arduino, we try to avoid working with fractions, and that wouldn't be very precise with volts. So I will be noting millivolts here. Now, for a little bit of magic, we just stuff these 2 samples directly into the map functions and output that to serial. And we are done. Pretty cool, right? But wait, there's more. The R1 and R2 do not have to be 1 on 1. Look at this chart to see what happens if we make R1 a bigger resistor. The bigger R1 compared to R2, the higher a voltage we can measure. Now we can finally monitor that battery, like we wanted. This is the second circuit. It looks a lot like the previous one. My power supply cannot go negative, so I switched the wires and now it can. Instead of a common ground, I connected the ground of the supply to the 5 volts of the Arduino. The power supply can now go from plus 5 volts to minus many volts. We can now see that when we lower the voltage at the Arduino starts to drop. Now the voltage is below zero, but the Arduino still reads within limits. Until we reach minus 5 volts, and the Arduino gets 0 volts. Just like the previous example, I will get me some data points and put them into the code. You can see the Arduino following the voltage, but it is a bit off. Why is that? Well, calibration is a precise process, and a breadboard is never precise, and neither am I while trying to film. Back to the charts. With R1 equal to R2, we can read voltages from positive 5 to minus 5. But if we use a larger value for R2, we can extend the range a lot. The third circuit. This one required even more trickery from my power supply. Now I have 2 of them connected with a common positive. This means I can now go from positive 15 volts to minus 15 volts. For the circuit, we now have 3 resistors. 2 equal resistors, one from Arduino to ground, and the other from Arduino to positive 5 volts. A third and bigger resistor from Arduino to the voltage source, which is now my power supply. Without the supply on, the Arduino will default to 2.5 volts, because of those equal resistors. Any voltage on the supply will pull that voltage either up or down, but not too much, because that resistor is bigger. No need to do the coding and charting again. That is basically the same as with the previous circuits. This final circuit is an amplifier. It can make smaller signals big enough to read with an Arduino. And even this amplifier uses a resistor divider. Those things are everywhere. That thing in the middle is an operational amplifier. The chip has two of them, but we will use only one. To understand this circuit, I will simplify the working of the op-amp. Three things can happen. Is the plus input bigger than the minus? Increase the output voltage. Is the plus input lower than the minus? Decrease the output voltage. And if both are equal, maintain the output voltage. The output is connected directly to the minus input. That makes this a voltage follower. Because the minus input will always move in the direction of the plus input. In our circuit, we again use a resistor divider. With equal resistors, the minus input only sees half the voltage of the output of the op-amp. The op-amp still does the same routine, but it has to output double the voltage to get the inputs at the same voltage. And finally, increasing the value of R1 compared to R2 increases the amplification of the input signal. Thank you for watching.